definition of antiderivative. So, derivatives is what we've been doing for the first 3 chapters. So when you hear the term antiderivative, it should, somewhere in your brain, think it must be the opposite of derivative, right? And so it is the inverse function pretty much for derivatives. You're working backwards is what you're doing. So you can think of it as you've been given a function and you're finding the derivative, and now you're actually going to be given the derivative piece and you're finding the function back. So you're actually working backwards, okay? So there are some notation things. If f is the antiderivative, so you'll notice this is a capital letter F, of f little script f, that is the original function on the interval I, then g is an antiderivative. Notice both of these say an. If and only if g is in this form, f of x plus c. So we're going to talk about basically antiderivatives that are indefinite and antiderivatives that are definite. And so we're going to start with indefinite integration, as you can see from the title of this section. And the reason we start with indefinite integration is because you have really multiple functions that can derive to the same function is what ends up happening. And so if you look, you'll see that it says find the general solution of a differential equation. And so they have told us that y prime, which is our derivative, equals 2, okay? And so if you think about your rules of derivatives, the only way I can get just a constant is if, first of all, the degree of my prior function was a 1. Because remember, when you have like just an x and you take the derivative, you get the coefficient in front of x, right? Mm-hmm. And so now we're working backwards. So instead of starting with the function and taking away an exponent, we're going to start with the coefficients and we're going to add an exponent. And so this one would be 2x, right? But here's the issue with 2x. I could have had a constant added to it, right? And so they've given me examples. This little line here is just y equals 2x. That's assuming that my y-intercept was 0. This is a constant of 2. So this next line would look like this. This one right here is a constant of -1. And so this guy would look like this. What you'll notice about those 3 functions is if I took the derivative, every single one of them would give me a derivative of 2. Right? My 2x would go to 2 and all of those constants would go to 0. All right, and so this is what we're talking about when we say a general solution. A general solution then just takes that antiderivative and it accounts for any constant that you could possibly add to it. So this is what you always want to do to indefinite, is you want to say a plus c. All right, if you do not know your initial condition, which we're going to get to that, then you have to assume that it could be a constant added to it, even if that constant is 0 per se. So we'll just, looking at this, until we start getting to definite integration, you're going to have to remember that plus c. So notation for antiderivatives, all right? We have typically dy dx, and especially when you do implicit differentiation, remember dy dx is going to be your derivative, like the derivative of y with respect to x. So when you think about this, they write it in equivalent form, dy equals f of x dx. So very often you will see this little guy right here, f of x dx. It actually comes from your dy dx format. This is telling you this is my antiderivative with respect to x. All right. And so we have to find my, or this is my derivative with respect to x. So to find my antiderivative plus c, I'm taking it with respect to x. This is important right now because later on, just like you did implicit differentiation with multiple variables, there will come a time when we use multiple variables for integration as well. And so you need to pay attention to what am I integrating with? Which variable am I integrating with? Because you do want your variable here that you're integrating with to match the variable that you are taking the dx of. All right, so this left side is all the derivatives you've already learned, okay? The derivative of any constant is 0, all right? So then if you look to the right, if you were to integrate 0, then that must be a constant. That's the only thing that's going to, the derivative is 0. So basically, this is saying the derivative of this is what? And this is saying, I've given you the other side of it. The antiderivative then goes backwards, okay? So this little symbol right here means that you're integrating. You're taking the antiderivative, okay? It looks like it would be in your music somewhere, but that's what it is. So then we've already done this. Some constant times x, when you take the derivative, you get a constant, right? Well, then if you take the antiderivative of a constant, it's that constant times x plus c, right? See this little guy right here. When I have a constant in front of a function, I just take the derivative of the function and multiply it by the constant. Let's say 3x squared or something like that, right? You just multiply by that 3. The same is true here. When you're taking an antiderivative and there's some constant multiplying, you can pull it out in front. And you can do the antiderivative first and then multiply your answer by the constant. When you're adding and subtracting pieces of it, 3x squared plus 2x plus 4, and you take the derivative, you can take the derivative of each piece, right? Same is true of antiderivative. You can take the antiderivative of each piece. Okay, here's where we start getting into our rules. We have a variable raised to a power. What do you do when you're taking the derivative? Well, you multiply by that guy, and then you subtract 1 from it, okay? You work the opposite here. For antiderivative, instead of multiplying and subtracting, you add and then divide. So you go in the opposite order. You multiplied, then subtracted, and here you're going to add and then divide, okay? And then we get into our trig functions, all right? The derivative of sine is cosine, so the antiderivative of cosine is sine. The derivative of cosine is negative sine, so the antiderivative of sine is negative cosine. They flip-flop there, right? Derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. Everybody see how we're doing this? So this left side you have memorized. The right side, think of it like logarithms. The answer is now what you're given, and you're working back to the original. All right? All right, so we're looking at this. It says here's a solution. We want to integrate 3x. We can pull the 3 out, right, and just take the antiderivative of x. So I have 3x here, and I want the antiderivative. What is my exponent on that x? It's a 1, right? So my rule says I'm going to add 1 to it, okay? What is my new exponent? Divide by your new exponent, all right? So another way to write that is 3/2 x squared. And then since we're doing antiderivative, I always have to do this little guy right here. So this would be my antiderivative. Special things you may want to rewrite, okay? This is 1 over x cubed. Well, if I'm trying to manipulate exponents, x to the -3, square root of x, again, x to the 1/2. 2 sine of x, pull that 2 out in front, and all you have to worry about is doing the antiderivative sine. So if I look at this, -3, add 1. What's my new exponent? X to the -2 divided by -2, all right? This x to the -2 needs to go on bottom with that 2 on bottom, so -1 over 2x squared plus c, right? X to the 1/2, if you add 1, your new exponent is 3/2, and you divide by 3/2. When you divide by a fraction, you keep, change, flip. So that's 2/3 x to the 3/2 plus c.
So will we put plus c for b?
Same thing here. Pull the 2 out. The antiderivative sign is negative cosine. -1 times 2 is -2 cosine of x plus c. So we're going to rewrite x to the 1/3. All right. My new exponent is going to be x to the 4/3, and then I'll divide by 4/3, right? That's keep, change, flip. So it's 3/4 x to the 4/3 plus c. Okay. All right, integrating polynomial functions. You have pluses and minuses going on. All right. This just looks like it's missing something, right? It's like, what? What's going on here? If you don't see anything, what is it? It's a 1, right? So really, this is just going to be add in your x, 1 times x plus c, okay? Anytime you have a constant, your antiderivative is going to be the constant times x, all right? So like for this one, it broke it up, but you don't have to write it out like that. Look at each piece individually. How would I do the x? Well, my new exponent is going to be x to the second power divided by 2. So that's 1/2 x squared. And then my 2 is a constant. So it's going to go from 2 to 2x. And then, of course, I have my plus c. All right, let's look at the next one. My new exponent is going to be 5, right? And it is divided by 5. My new exponent is going to be 3, and then it is divided by 3. And my new exponent here is going to be 2, and then divided by 2. Okay? So that's all you're doing with your exponents. Add 1 and then divide. All right? Any questions on polynomials? All right. Try this one. On this one. So it's x squared, and then I have 2 over 2. So what am I going to do with that? Yeah, it's going to be x squared minus, what happens to this guy? My new exponent is 3, and I have 3 over 3, and then plus c. So reduce it if you can. So you have something like this that looks a little crazy. You're going to want to rewrite it before you start integrating it. So they've given you this right here, x plus 1 over the square root of x, and you're like, quotient rule, like what's going on here? No, each piece of the numerator is just divided. So that x is divided by square root of x, that 1 is divided by square root of x, all right? Something like this, it's x to the first power over x to the 1/2, right? So what do I do when I'm subtracting like bases? I mean, when I'm dividing like bases, I subtract. So 1 minus 1/2, this is going to be x to the 1/2. This is in the denominator, so this guy is going to be x to the negative 1/2. Right? And then now I can integrate it. Add 1, that's going to be x to the 3/2 divided by 3/2. Add 1, negative 1/2 plus 1 is x to the 1/2 divided by 1/2, right? And then plus c. Trig functions. All right, sine over cosine squared. So when you have trig functions, you have to look at manipulating it first potentially, okay? We will do some substitution where you can potentially do something like this, derivative of cosine is sine, and we can do what's called u substitution. But before we get to that, so if I look at this, I have sine over cosine squared, and they've split it up into 1 over cosine and sine over cosine. Well, then you're thinking, how does that help me? Well, 1 over cosine and sine over cosine actually are trig functions. So if I rewrite those, 1 over cosine is actually secant. Sine over cosine is actually tangent. So I want the antiderivative of secant tangent. Well, that should sound familiar because that is a derivative that we have learned. The derivative of secant is secant tangent. So then the antiderivative of secant tangent is just secant. So why are initial conditions important? Well, we talked about it earlier. That c could be anything. You could have a -3, -2. This same function, and they've given it right here, derives to x cubed minus x plus c. This is what the function looks like, but depending on what that c is, it could be anywhere on your graph, depending on what that constant is. And so the constant that you're looking for is really called a particular solution. If you can get that constant, then you no longer have a general solution, which could be a multitude of answers. You now have what's called a particular solution. But in order to have a particular solution, you have to have more information than what you have been given. And so you can find this if you are given what's called the initial condition, all right? They have to give you some condition that helps you solve for your constant. And so, for example, we found the general solution right here, capital F of x rather equals x cubed minus x. Then they gave us this little extra bit of information. This little extra bit of information is the initial condition. They said, well, if you plug in a 2, you get 4. Well, that helps us because we can plug in a 2 and set it equal to 4, which is what they did. They plugged in a 2 here, 8 minus a 2 here, 2 plus c that we don't know equals 4. And then they just solved it. 8 minus 2 is 6, subtract 6 over c equals -2. And then they rewrote it, and instead of writing a c, they wrote -2. Okay, and so this is called a particular solution. Particular solution because we no longer have a general solution here, all right? So with indefinite integration, you will always solve for a general solution unless they give you an initial condition that helps you solve for it. So let's look at this. Find the general solution of this guy right here that satisfies the initial condition of f of 1 equals 0. So the first thing we have to do is integrate it. So we have to figure out what my f of x is. So if I rewrite it, this is x to the -2. So my new exponent is going to be what? Add 1, it's going to be x to the -1, and then divide by -1, that gives me -1, right? Rewrite it back, because that's ugly. So -1 over x plus c. That is my function, all right, that I'm looking for. Now they've given me more information. If you take that function and plug in a 1, you get 0. So let's do it. We're going to say f of 1 we now know equals 0. Well, f of 1 is what happens when I plug in a 1. -1 over 1 plus c equals 0. -1 plus c equals 0. What is c? 1. So now I can rewrite it using my particular solution here. My function looks like this. F of x equals -1 over x plus 1. All right. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving the height s as a function of the time t. When does the ball hit the ground? So my initial height is 80. My initial velocity is 64. All right. When you have these, you start with an initial acceleration of -32. The reason we start with an initial acceleration of -32 is because we are in feet, and -32 feet per second is the acceleration due to gravity. Okay. So they have actually, we're going to have to assume our second derivative is -32. All right. So I need to find the antiderivative of this guy first. All right. So acceleration, remember acceleration is second derivative. So if I find an antiderivative, I'll actually be working backwards. So remember it's position, derivative of that is velocity, derivative of that is acceleration. And so I'm actually working the other way. All right. So the antiderivative of this is going to be my velocity function. So it's just a constant. So my velocity is going to be -32. What do I do with a constant? except I'm with respect to time, so it's going to be t plus c, right? They told me my initial velocity, didn't they? What is my initial velocity? 64, all right? 64 feet per second. All right, so initial, if they don't tell you, you can assume it's at time 0, all right? So that means at time 0, my velocity should be 64. So what is c then?
64.
By the way, if they give you an initial velocity, it's usually going to be your c, all right? Unless they say after 3 seconds, but all right, c. So that means my velocity function looks like this, negative 32t plus 64. Now I want to find my position function. Well, my position function should be the antiderivative of velocity, right? So now I'm going to do antiderivative of velocity. I'm going to do the antiderivative of this guy. All right. My new exponent is what? T squared. Negative 32 divided by 2 is negative 16. Plus 64t plus c. That is my position function. But I need to put my initial condition here. They told me my initial position. What is it? 80. By the way, if I do 0, 0, my c is going to be that 80. So my position function is going to look like this. That's my position function, all right? So I have found my velocity function. I have found my position function, okay? And acceleration was just negative 32. Now they've asked me another question. We found the position function, but they want to know when the ball hits the ground. How do I know when the ball hits the ground? What's the height of the ball when it hits the ground? 0. Which position or velocity, which one tells me the height? Position. So all I have to do is set this guy equal to 0. Negative 16t squared plus 64t plus 80 equals 0. Set it equal to 0 and solve. You can actually, by the way, factor out. What comes out of all three of those? Anybody know? Yeah, 16 does. And I would actually take out a negative 16. You get t squared. How many times does 16 go into 64? 4t. How many times does it go into 80? 5 times. So I get t minus 5, t plus 1, right? I have a time of either 5 or negative 1. I'm talking about time in seconds. One of those naturally does not work. Yeah, we don't time travel. So it's after 5 seconds it's going to hit the ground.